Hello and welcome to Say That Again Slowly, the Cambridge Festival podcast where students at Cambridge University chat with experts who have contributed to the festival. We try to pair up students with researchers and authors from very different disciplines to bring things back to basics. So there are no stupid questions here. My name is Joanne Yau and I'm a first-year undergraduate student studying human, social, and political sciences. Today, I'll be interviewing the team behind Atomic Academy, who are running a stand at the Department of Engineering from 10 a.m. to 4 p.m. on the 23rd of March. So starting off, I'm just going to thank you for coming to chat with me today, everyone. Could you please introduce yourselves and what you do?
Okay, so I am Jason. I'm doing a PhD as part of the material selection process for the new fusion power plants of the future. So I specialize in the corrosion of stainless steel, and I hope to include the effects of radiation damage onto it.
Cheers, Jason. So I'm William Thomas. I'm doing my PhD at the University of Bristol. My PhD is in condensed matter physics and material science, focusing on advanced fuel types and also how we can use different types of fuel waste to incorporate into new devices.
Thank you. And maybe have Martin.
Yep, hi, I'm Martin. I'm doing my PhD at Imperial College London in looking at basically how stainless steels that you'd find in nuclear reactors break. And that is to eventually make reactors even more safe and more durable and save millions of pounds, hopefully.
My name's Hannah, and I'm also from the University of Bristol. And my PhD is studying the effects of thermal plasmas on the structural material of fusion reactors.
So I'm Parth Kulkarni, and I'm doing. I'm in my second year of PhD, and I'm doing it from the Open University under the NEF CDT, and I'm looking at characterizing fusion materials, diverter materials for fusion reactors.
Thank you. So let's start with some basic questions. Can someone explain what nuclear power is and how it is produced?
I can take the floor on this one. So nuclear power involves the splitting of large nuclei. So the usual nuclear fuel we use is uranium because it has 92 protons in the nucleus, making it an extremely large nucleus. And the large nucleus interacts with a slow neutron or a low energy neutron, and this causes the atom to split, not equally in two, but into two different parts. And during the splitting of this atom, there's a large amount of energy produced. And we harness this large amount of energy by heating up water and producing steam to turn a turbine, which is actually the same way electricity is produced for when you use fossil fuels. But the energy density when you use uranium as a nuclear fuel is much larger than that of other fossil fuels.
Thank you. And in layman term, I'm just wondering, say, for instance, what Martin you're doing in layman term, and what is a fusion reactor and how does it work?
I think for fusion, it's better to speak to Jason, but I can talk more about what I do.
Yeah, certainly you can do the splitting in that way. Yeah.
Okay, sounds good. Right, so in practice, I'm just taking blocks of stainless steel, the same ones that you'd find in the cooling circuit for a nuclear reactor, and I put them in a machine and I break them over many, many, many cycles. And then I try to record as much data as I can, so that can be, literally having a camera recording that block of metal as it breaks, or things like the load you're applying, things like that, or even running a current through it. And putting all these things together, the goal is to really understand how this material behaves, how it's going to break, and over how long in these conditions. So that way, if we find a crack in the cooling circuit of a reactor, we can say whether we need to shut it down or whether it's actually safe to run it for a bit longer. And the idea is that you can extend the life of reactors that we thought were done with their life, and that lets you save a lot of money over building a new reactor, and it's also pretty much essential if we want to hit those net zero, these net zero goals that we have for 2050. So it has this sort of dual purpose here.
Thank you. And maybe Jason elaborating a bit on what fusion reactors are and how do they work.
So I'm not really an expert in fusion reactors per se, but more to do with what happens to the materials that are in them. Fusion, as we know, it differs from fission in the sense that instead of splitting a heavy nuclei, we combine two lighter nuclei to release energy. Some of the ways that we try to do fusion, we will be bringing an example of one of the hobby methods is, for example, creating a hot plasma of hydrogen, so deuterium or tritium, and we can see the effects of having this very, very hot plasma. We can reach the critical temperature for these two to fuse. So we will be bringing a fuser to this festival. In terms of my work specifically, it should be noted that when you have a plasma that's hotter than the center of the sun, the materials that are exposed to it are definitely going to take a beating. Not only that, but also same as fission reactors, we have to deal with a high neutron flux. So radiation can actually damage materials, and especially for a fusion reactor, it takes something like 100 times the average neutron flux of a fission reactor. So you can tell that it's going to be an extreme challenge to find materials that are suitable for this environment.
Okay, I see. Just a bit more on fusion reactors, if I may. What is the difference between structural and diverter materials?
That one I'm not quite an expert in either. I can tell you that there are different material requirements for a fusion reactor. So, for example, if we take a simple plasma-based fusion reactor, we have to have in the inner lining, it has to maintain. It must survive the extreme temperatures, especially when the plasma, for example, fluctuates and it may collide with the wall. It also has to survive the extreme neutron damage. Not every material can do that. And it differs from structural materials. So structural materials, you're looking at about the outer edge. So most notably, the stainless steel, for example, or you have pipings. When we eventually want to consider how we're going to extract energy from this fusion reactor, we have to consider much more external materials that may share some similarities with how we run our fission reactors right now.
Okay, thank you very much, Jason. And since you mentioned, maybe I'll pass this question to somebody else, but as you mentioned earlier about fission. So what are fission materials and how does that work as well?
I'll
You go for it.
Yeah, so I mean, a fissionable material is one with an unstable nucleus due to it having such large mass. And in order to make it fissionable, it needs to absorb a neutron, but instead of undergoing a process such as transmutation, where we would actually obtain a different element, the nucleus splits. So that is the definition of something that's fissionable. It's if it interacts with a neutron, the nucleus will split and release energy.
Okay, so sort of in brief, what is the main differences between nuclear fission and nuclear fusion?
Okay, so nuclear fusion involves, so we're talking about really small atoms here, such as hydrogen, and due to larger nuclei, such as helium, being more stable, they actually emit energy when they fuse. So that's the difference. In fusion, it's the combination of two small nuclei, whereas in fission, it's the splitting of one large nuclei. But in the end, the same result. It's due to the final product being more stable than the initial. So you need to give off a little bit of energy to attain that final state. And that's what we harness in these reactors. And I mean, the one thing Jason maybe missed out on fusion is there's the really big fusion reactor we know is the sun in the sky. And the sun uses its fuel, which is hydrogen, and it just does fusion on an enormous scale.
Okay.
So the reaction that we see in our reactors is actually the same as that we see going on at the sun.
Okay. So sort of looking forward, what is the anticipated future of nuclear and fusion? Just kind of an open question to anyone.
So in terms of fission, I think currently we're looking at small modular reactors, and the benefit of this is that it doesn't require the high capital costs as conventional nuclear power plants. So if you can produce them en masse as well, that increases the certainty that we have in its reliability and its ability to be mass produced, means that we can cut down costs quite a bit. So that's an exciting field that's coming along. Another field in fission reactors is we're taking a second look at the next generation of nuclear reactors, such as the HTGR. So these are reportedly safer because they do not have the issues that a traditional PWR would have. So these acronyms, HTGR, high temperature gas cooled reactor. So some examples might include the HTR-PM that recently came online, as opposed to PWR, which are the ones that France currently uses. So in terms of the fusion reactors, those are still being developed. There are a lot of smaller companies which have branched off, and they are trying their own individual take on how to reach the net fusion power again. But we are still some ways away.
Thank you. So let's move on to something else. Jason, you'll be doing a cloud chamber demonstration at the stall. So what exactly is that?
So a cloud chamber is quite a cool kit, which allows you to sort of see the effects of radiation. So I actually tried to build one when I was an undergrad, and it's quite a tricky bit of tools to build. So essentially what you have is you're making a super saturated fog of isopropyl alcohol. And the reason for this is because you want to, well, as the name suggests, you want to form a cloud. And what this allows you to do is that when you have a bit of radiation coming along, it might ionize the gas or the molecules in that cloud. And these ionized molecules act as sort of like seeds. So when you imagine seeding a cloud, like how we cause rain nowadays, so we form an artificial cloud within our chamber. And because these particles, they ionize and they travel in straight lines, you can see these sort of lines of clouds forming within your cloud chamber.
So in practice, it lets you sort of see the natural radiation that's all around us as sort of little beams appear in the chamber, and it's completely safe, but it looks really cool.
Okay, so since Martin, you mentioned briefly, it's kind of what I'm trying to lead into as well. How does radiation actually affect us in everyday life, and is it safe for us to be in contact with it?
Yeah, so the short answer is yeah. So there's a bit of a stigma on radiation, isn't it? But it's really everywhere around us. It's probably next to all of us right now, just in very small doses. The way we understand radiation right now is that starting from a threshold dose, then we can actually start seeing effects in the human body, which can lead to problems. But most humans throughout their whole lifetime will never even reach that threshold dose. It's actually quite high. You know, that's why taking the plane, people say you get irradiated when you're on long flights. That is true, and you can keep doing that because you're not going to cross that threshold. And that's the same way we want to manage our reactors. We're making it so that everyone around is never going to be anywhere near that threshold dose, so that you don't have actually any effects on the body.
Thank you. So really zooming out to the big sort of problem here, or question, I should say, is nuclear power safe?
I'd say almost certainly now. in the types of designs, the reactors, so the considerations designers put into the reactor designs now make the reactors almost impossible to become unsafe unless there's a lot of fail-safes you'd have to overcome for this. There's obviously there's the famous stories, isn't there? Of course, we've got the disaster in Russia and the disaster in Japan, but because of these disasters, we've actually learned our lessons, and we've learned them very well. So when they were designing these reactors maybe 50, 60 years ago, there's some things that they wouldn't have considered, but now these are at the forefront of our design considerations. So most of the fuels we use actually, as they increase in temperature, their reactivity decreases, which is not something that was considered in previous designs. And there's also ways where, so in Japan, for example, the reason for the meltdown was there was a loss of water, and this loss of water resulted in the fuel getting too hot. But now actually people have designed ways to cool the fuel using just air. So we don't require pumping, but we just require the natural circulation of air, which actually provides enough heat transfer from our fuel, and this prevents a meltdown.
It's worth adding that.
Sorry, it's just important to note as well that if fusion becomes commercially viable and becomes something that we use in the future, it isn't even possible for fusion to melt down in the same way that a nuclear fission reactor has done before in the past. So even though it seems like quite a scary and alien concept, it's actually safer in concept than fission reactors ever were.
I agree.
And it's worth mentioning as well that the industry has been, is, and will be, for as long as we can think of it, be focusing on safety as the #1 priority. So whenever there is an improvement to make, the industry will be working towards it. So it's not just a thing that we can say it's safe and we're done. It's constantly being worked on more and more, and constantly being improved. And you know, the levels that we're at today are extremely satisfactory, but it's always going to be worked on more and more and more.
Yeah, so certainly it seems that nuclear power is pretty safe these days. Okay, so let us move on to something else we can. Well, maybe, what can you tell us about fuel and waste created by nuclear?
So, as I said earlier, the main fuel we use for nuclear is uranium, because it's a really heavy element, but actually, relatively, it's quite stable over a long time. So there's an abundance of it on Earth. But we're quite stuck in our ways of we use a fuel called uranium dioxide, because this is what we've been used to since maybe the 1950s. But actually, when you look at different uranium materials, it's actually not as efficient when compared to things like when we react uranium with nitrogen to get uranium nitride, or actually react it with carbon to get uranium carbide. So we're trying to always develop new types of fuels which allow us to transfer heat better and actually have higher melting points. But the other question with waste is, uranium dioxide has been used as a nuclear fuel for almost 60, 70 years now. So that means there's a lot of it just stockpiled up. It's not being used. And actually, some of my work looks to take this waste product and actually convert it into something that's useful. So, for example, uranium is actually extremely good at storing hydrogen. And it could be another argument for nuclear that even though we're using this fuel and we're arguably wasting it, there is still use for it afterwards. Whereas if you talk about fossil fuels, then the only thing you're talking about is greenhouse emissions, and nobody wants that.
Okay, so on the topic of waste, more for our general audience, what is the main difference between nuclear energy and fossil fuels like coal or oil?
So in terms of waste?
Yeah, in terms of waste or other sort of main differences as well.
Mm-hmm. Yeah, so nuclear waste it's mainly a really hot material that's just come out of a reactor. So it's either really hot because of there's fission products. So this is a fission product, is something that's left over after a fission event. And because of the high energy associated with the fission, these remain really hot. So the first stage of waste is actually cooling this down. So we store these in ponds for 5 to 10 years after they're directly used in the reactor to allow them to cool down. Then after that, most of the really harmful things have decayed away, but it's still quite harmful to human health if you were to be in the close vicinity.
I just want to add that is for just to add a tiny point. That's just for the worst case of waste, right? That's what we call for high level waste, right?
High level waste, yeah.
Yeah. So most of the waste will not be hot. But sorry, yeah, I just wanted to make sure.
No, it won't be hot, but it will still be irradiated and produce some radiation that will be harmful to us. So we endeavour to find new ways to store the waste safely, and it turns out concrete's a pretty good way, and just any rock in general. So that's why we've considered to store all of our fission waste underground in disposal facilities. And yeah, I mean that's the way the waste is going to go in the future. I think we'll store it all underground. But there's again the safety considerations to make this safe. There's a lot of them. There's a lot of good people working.
Yeah, and so in terms of its comparison with fossil fuels like coal and oil, how would you compare, especially in terms of like environmental impacts?
Mm-hmm. Yeah, so the waste with fossil fuels is mainly just carbon dioxide gas, and it's actually quite a challenge to store this. I know there is a big push actually in the UK to develop our carbon capture, but I think this might actually be sort of an excuse for us to continue using fossil fuels. Because the waste is difficult to store as a gas, and it's hard to leach out from what you actually want. But there are no benefits to the waste. It's actually quite carcinogenic, some of the byproducts of burning fossil fuels as well. Whereas, as I've said, some of the waste from nuclear can actually still benefit us in our lives every day. So I'd say that's an advantage to using nuclear over fossil fuels there as well.
So sort of again zooming out to the big picture. Overall, is nuclear power green?
Depends how far back in the life cycle you'd like to go. Because if you even talk about renewables that we all consider green, the mining processes, which is probably accounting for the most emissions from nuclear, are very high for renewables also. So if we want to focus on mainly the fissioning of the fuel, then it is completely green. There are no greenhouse products when you use nuclear fuel. The only thing would be is when you use fossil fuels to power mining production and stuff like that.
Okay.
Which is inherent in all fuel production.
Is there anything that anyone else would like to add on to that question?
Yeah. So when you talk about green energy, you've got to consider that the goal ultimately is to address global warming, right? That's why we're talking about this. And in that sense, you know, all of the reports that we've seen at the COP conferences and things like that point towards nuclear. You know, there's a pretty big consensus that nuclear is essential into reaching, in fighting global warming. And so, although it might not be as let's say carbon efficient as some other technologies, it's definitely up there, and it's essential to addressing that. Yeah.
Okay, so finally going back to our main topic of the Cambridge Festival, can you guys tell me a bit more about the stall that you guys are going to set apart from like the cloud demonstration? What other main activities would there be at your stalls?
So for this festival, we are going to have 4 stalls, and they're focused on 4 different parts of the nuclear industry. So the future of nuclear and of energy in the UK, energy waste and the environment, the drive a reactor stall itself, where you'll get to see a simulation of what it'd be like to drive a reactor, and the last one of radiation in everyday life, which is part of Jason's cloud chamber piece of kit. And essentially, we've got sticker sheets and worksheets, and there are going to be 4 stalls set up where you can go, you can collect the sticker to say that you are now qualified in this area of nuclear. You can chat to us as you go, and hopefully just be an all-round learning experience for people who don't quite understand nuclear yet.
That does sound really interesting for the general public. And with the simulation and like the connections to everyday life, do you think that science is best communicated through interactive activities like that?
I think definitely. So in the radiation in everyday life bit, there's also a simulation of how Geiger counters work, and the fact that even bananas are radioactive. So in terms of what you're experiencing in your life around you, it's nothing to be scared of. And when you put it into context with things like nanas and flights and even like living next to a nuclear reactor isn't as severe as the effects you get from those already two everyday things. And I think when people experience that and when they're able to see it in person, I think it helps them feel safer in their environment.
Definitely. Is there anything that anyone would like to add on with like the stalls or sort of the festival overall?
Parth, would you like to talk about your stall and about what you're doing?
Yep. Yeah, so I'll be on the Nuclear Future stall, and we'll be showcasing what nuclear fusion is through we'll be setting up something really interesting to watch at and a prototype of what a fusion reactor would look like. And kids would especially enjoy looking at the bits like a Lego set. So it would be really enjoyable. And the bit I'm working on right now, I would describe it as because fusion reactors produce a lot of heat inside the chambers, this heat and the ash that is produced during the reaction needs to be extracted out. And this is done by a component in the fusion reactor called as a diverter. And it can reach up to a temperature of, let's say, 2000 degrees at peak operating ranges. So to cool this down, we use different sort of pipes, and the material of these pipes hasn't been fully understood yet. So the mechanical and high temperature behavior hasn't been understood, and that's what I'm working on as my PhD project.
Okay, thank you. So I think that brings us to the end of this little podcast. So thank you everyone. Please do come along to the Atomic Academy stand at the Cambridge Festival, which will be at the Department of Engineering from 10 a.m. to 4 p.m. on Saturday, the 23rd of March. And please make sure to follow the Cambridge Festival on Facebook, X, and Instagram for more fascinating events.